We'll get to it. Right. There we go. Okay, so we left off somewhere around here, around valence bond theory. And you should know that when you have two atomic orbitals that overlap to form a bond, it's kind of akin to overlapping waves, where they can overlap constructively or destructively. And when we have constructive interference, meaning the waves are overlapping in phase, that's what results in a bond. And again, the book goes into a little bit more detail about that. And you should understand what a sigma bond is. And a sigma bond is formed by the direct overlapping of two s orbitals, or the head-to-head overlapping of two p orbitals, or an s and a p orbital overlapping. So here we have an s orbital. This orbital is an s orbital, and this is an s. So we have them overlapping. But again, like I said, you could have an s, right? This is an s orbital. You could have it overlapping with a p, like this. So if I was to take a p orbital, I'll just demonstrate here. Here's my pencil. If we were to take an s orbital, and then if it overlapped with a p, like that, that would make a sigma bond. Or if you had two p orbitals overlapping head to head, let's say I had a p orbital. Nah, it's not a good looking p orbital. Let's say I had one like this. There's one. And then if I have a second one like this, so this is a p, this is a p. So let's say they overlapped like this, head to head. That would also result in a sigma bond. Okay, so this would be a sigma bond. Ooh, where's my red pen? This would be a sigma bond, right? This would be a sigma. This would be a sigma. And of course, when we have the overlapping of orbitals to make a sigma bond, how many electrons do we share to make a bond? Anybody? It's not a trick. How many electrons in any bond? Exactly, there's two. So if you remember back when we talked, when you learned hybrid orbital theory in General Chemistry 1, you might have seen them draw, two electrons where the overlap is, and you could do the same thing here. It all means the same thing. Can I ask you guys a question that would take a little bit more text to answer? Could anybody tell me, what does it look like when I have two p orbitals that form a pi bond? It's not really what we're talking about at the moment, but I thought I'd just quiz you on this. What does it look like when I have two p orbitals? How do they overlap to form a pi bond? Because so far, all we're talking about are sigma bonds. Did anybody answer that? When I form a pi bond, what does the orbital overlap look like? Anybody know that one? Exactly. Thanks, Katana. Great. So this is just something I wanted to test you on. All right, if I take a p orbital like this, okay, and I take another p orbital like this, okay, and when I overlap them side to side, like that, that forms a pi bond. Okay, so side to side overlap, that forms a pi bond. Anyhow, we'll get into pi bonding a little bit more later on, but I just wanted to make sure everybody was aware of that. All right, so again, going back to this whole concept or notion of constructive interference, let's say when we overlap our two s orbitals, so again, let's say we have a 1s1 orbital here and a 1s1 here, right? These are two hydrogen atoms, right? This is a hydrogen, this is a hydrogen, then we overlap them to form a hydrogen molecule. When we take a cross section of the sigma bond, we get a circle. So we get a circular cross section, and that's when we have a sigma bond. If you were to take a cross section, let's say here or here, right, again, you'd get something that's circular. Whereas if you were to take a cross section of a pi bond, right, if you took a cross section here, you do not get a circle. Okay, so when you have a circular cross section, that is when you have a sigma bond. Well, next section deals with molecular orbital theory, or MO theory. I'm not going to go into much detail on this section. The reason why is it's not really covered a whole lot until organic chemistry 2. It goes into very little, or it comes up very little in this class. And if you're wondering, I thought that this section or this chapter was a review of general chemistry 1. It is. And so when you would have talked about MO theory in general chemistry 1, does anybody remember the diagrams where you had the sigma, sigma star, pi, pi star? Does anybody remember that? you had all these different orbital diagrams, and you would fill out the number of electrons and determine whether the molecule was paramagnetic or diamagnetic. Well, if you remember that, when we look at MO theory with respect to organic chemistry, what MO theory is used for sometimes is to predict reactivity of molecules. And again, something we don't really do a whole lot of until organic chemistry 2. And so really all you need to know is that when we take atomic orbitals, they can form molecular orbitals, and however many atomic orbitals we have governs the number of molecular orbitals that we have, and they're always equal to each other. So the number of molecular orbitals created is equal to the number of atomic orbitals that were used to form it. So let's say we form a hydrogen molecule, and we take two 1s orbitals. When we overlap them, since there's two atomic orbitals that I have in the blue circles, we're going to make two molecular orbitals. We can have a bonding molecular orbital and an anti-bonding molecular orbital. And again, this is something that we'll go into more detail in organic chemistry too. The anti-bonding orbital is the one that's higher energy. The bonding molecular orbital is the one that is lower in energy. And so we always start by putting electrons in the lower energy molecular orbitals, and then we start placing them into higher energy ones after that. All right. So again, I don't think I have any questions about section 1.8 really directly on the quiz. Maybe just antibonding, bonding. Antibonding is higher in energy. The number of atomic orbitals is going to be equal to the number of molecular orbitals, and kind of leave it at that. But a section that's going to be really important for us moving forward in this class is going to be anything that deals with hybridized atomic orbitals. So hybrid atomic orbitals. And if I just switch for a second here over to, just bear with me here, I'm going to go into here and grab a blank document. So if we think about, the electron configuration of carbon, so if we have carbon, which is 1s, 2, 2s, 2, 2p. Anybody? Could anybody finish the electron configuration of carbon for me? It would be 2p, how many? Yeah, 2p2. Thanks, Sean. All right, so 2p2. So we have a total of 4 valence electrons, right? These are the valence electrons. So 4 valence electrons. Now, if we draw out the orbital diagrams for those valence electrons, what's it going to look like? Okay, well, we've got 1 2s orbital, right? And then we've got 3 2p orbitals. So I've got 2 electrons in the 2s. For my 2p's, I've got 1 2 electrons. So what does that mean? If we have 2 unpaired electrons, what that tells us is that carbon can only form 2 bonds. But that doesn't make any sense. You're like, what? Well, why would that be? Because Mr. Dion, I remember that you told me not long ago that carbon always forms 4 bonds. And back in general chemistry, they taught me that the Lewis structure of carbon was a carbon with 1, 2, 3, 4 unpaired electrons so that it can form 4 bonds. So where do we get that from? Where this comes from is from hybridizing atomic orbitals. So these, again, are atomic orbitals. A 2s is a type of atomic orbital, and there are 3 2p atomic orbitals. They are all equal energy, the 3 2p, so we say they are degenerate. So how do we make 4 oops, where am I? Did I just delete everything? Son of a gun, where was I? Yeah. How do I make 4 unpaired electrons? Well, the answer is, what we're going to do is we're going to take one of the 2s electrons and we're going to move it into one of the 2p orbitals. And we call that hybridizing. So we hybridize. And what we're going to do at the same time that we put that 1 electron from the 2s into the 2p, we're going to mix the 1s, so we're going to mix an s orbital and 3 p orbitals, all 3 of those, and we're going to make 4 degenerate orbitals, 1, 2, 3, 4, and we're going to call them sp3 orbitals. And now we're going to have 1, 2, 3, 4 unpaired electrons. And there you have it, folks. This explains why we write the Lewis structure of carbon as it having 4 unpaired electrons, because you have 4 unpaired electrons that are in 4 degenerate orbitals. We call them sp3 orbitals. All right, just a couple other, kind of housekeeping items. We looked at what the shape of an s orbital is. It's a sphere. right? We looked at the shape of a p orbital. It looks like this, okay? So if you're wondering, well, what does the shape of an sp3 orbital look like? Well, I'm going to make it very simple for you, okay? The way that we draw an sp3 orbital is we just draw a big lobe like this. We actually, and this is not a joke, we label it. We write sp3 in it, and so that way there's no question. And if you're saying, well, shouldn't there be another lobe, right? Because there's a positive and a negative lobe. The answer is yes. We usually just draw something really small like this, but for our purposes, we can just leave it out. Okay, we just leave it out and we write the orbital and we say it's an sp3. And so now, if we were to draw the Lewis structure of our carbon atom, we would say here's our carbon atom, here's one sp3 orbital, here's another sp3 orbital, then I'm going to have one going in the back, and then I'm going to have one coming out in front like this. Okay, something like that. This is an sp3, this is an sp3, this is an sp3, and this is an sp3. They all have one unpaired electron in them, like that. And so that is why carbon has a tetrahedral geometry, molecular geometry, when it has 4 single bonds or 4 sigma bonds. And so now if we were to make a molecule like methane, which is the simplest possible organic molecule in the universe, so I'll draw the molecular geometry like this. Does everybody remember the tetrahedron, which has a bond angle of 109.5 degrees? Anybody remember that? Tetrahedral molecular geometry? Give me a thumbs up if you remember that word even. Okay, awesome. All right, so we have a tetrahedral molecular geometry. Well, what happens is, in order to form the 4 sigma bonds, right, we have 1, 2, 3, 4 sigma bonds. We have the overlap of the hybridized sp3 orbitals on the carbon atoms with the unhybridized 1s orbitals of the hydrogen. So I'd have a 1s here, 1s with an electron with opposite spin, a 1s here from this hydrogen. So I'll put hydrogen, and then I'll also write 1s in each one. So there's a hydrogen atom here, and this is a 1s, and there's my electron. And then I have a hydrogen atom here, and this is also a 1s. And so where are the bonds? This is the sigma bond, this is a sigma bond, this is a sigma bond, and this is a sigma. Because remember, a sigma bond comes from the overlap of orbitals. So we have the unhybridized 1s orbital, and then we have the hybridized sp3 orbital. Now, I've taught this class a long time, a long enough time to know that there's probably some people who are a little bit confused or a little bit unsure, or maybe some people are just like, yeah, I remember all of this from Gen Chem 1. That's totally cool. So what you're going to have to do is go back into chapter 1 and read chapter 1.9 very carefully, because it's a pretty deep subject, hybridization. But, you know, if I could give you the Sparks Note version of it, or if I could give you the quickest version of it, it would be this. It would be if you have a carbon atom that has 1, 2, 3, 4 sigma bonds on it, we'd say that it's sp3 hybridized. If you have a carbon atom that has a double bond and 2 single bonds like that, we would say that it's sp2 hybridized. And if you have a carbon atom that has a triple bond and a single bond, we would say that it's sp hybridized. So that's for carbon. But then if you're wondering, well, what about other atoms like oxygen and nitrogen? What about their hybridizations? It's the same rationale, right? Because when we're talking about regions of electron density, or REDs as I like to call them, if you have a single bond, that counts as a region of electron density. If you have a double bond, that counts as one region of electron density. If you have a triple bond, it counts as one region of electron density. And if you have a lone pair, it also counts as a region of electron density. So if we have 4 regions of electron density, we have sp3 hybridization. So 4 REDs. Okay. If we have 3 regions of electron density, it's sp2 hybridization. And if we have 2 regions of electron density, or 2 REDs, then we have sp hybridization. So let's go back to this. If a single bond, a double bond, a triple bond, or a lone pair, if each one of those counts as 1, let me ask you a question. If I have a nitrogen that has 3 single bonds and 1 lone pair, could anybody tell me what is the hybridization of this nitrogen? This is just a question for you. Absolutely, right? It's sp3. Okay, let's try another one then. What if I'll try to leave this up here so you can see it. What if I have an oxygen that has, I don't know, a double bond and two lone pairs, something like this. So we'll draw formaldehyde here. What would be the hybridization? Sorry, I can't even see my own lone pairs here. Let me redraw them. If I have this oxygen with two lone pairs and one double bond, what's its hybridization? sp2, absolutely. What's the hybridization of this carbon? It's got a double bond and two single bonds. Anybody? Yeah, there we go. sp2 as well. Okay, so there you go. So that's like kind of the Sparks Notes version, excuse me, of hybridization. So let's go back into our lecture slides. Just bear with me here. There we go. Where were we? Somewhere down here. Just sometimes it's nice to kind of clear the slate and just go back to first principles. So what we just covered is everything that's on this slide, okay? How can we draw methane as a tetrahedron, right? How can we say it's got a tetrahedral molecular geometry? It's because you have 4 electrons in degenerate orbitals. Again, those are the 4 sp3 hybrid orbitals. So we explained that right here, and I showed you where these 4 degenerate sp3 orbitals come from. I showed you how to draw an sp3 orbital, and that explains the tetrahedral molecular geometry of methane. So again, in case you didn't catch that, methane is CH4. It is the simplest organic molecule in the universe, okay? 1 carbon and 4 hydrogen atoms. So let's move on from there, and let's just review that again. If we look at that sp3 orbital, right, it came from 1 s orbital and 3 p's, so it's 75% p character, 25% s character. And so you can draw the sp3 orbital the way that it's shown here on this slide and write sp3 in it. But again, for our class, I'm just going to draw an orbital like this and just write sp3 on it, okay? These two things mean the exact same thing, so we'll put a little same as sign here. All right. Now, if we have our 4 sp3 hybrid orbitals, each one has 1 electron. I showed you how to overlap each one of those with the hydrogen to make the sigma bond. So again, this is a sigma bond, this is a sigma, this is a sigma, this is a sigma. You should understand, or at least have memorized the bond angles for a tetrahedron is 109.5. And the next thing is, what if we have a carbon that has a double bond and 2 singles? Well, you guys already told me that this is sp2 hybridized, right? So where does that come from? Well, it's the exact same rationale, except now we only need to hybridize 1s and 2 p's. And so we take 1s and 2 p's and we mix them together and we make 3 degenerate sp2 orbitals. So that means that one of the p's that I'm going to circle in blue here, this one did not undergo hybridization. So it just remains as a plain old 2p orbital. Well, if you're like, well, what the hell is that for? Well, there's a very good reason, because if I look at the ethylene molecule, who remembers this? The first bond between any 2 atoms is a sigma bond. What's the second type of bond? What's the second bond? And it doesn't matter if it's the top or the bottom, that's irrelevant. It's a pi bond, right, Katana? This is a pi bond. And where do we get a pi bond from? A pi bond comes from the overlap of unhybridized p orbitals, right? The side-to-side overlap. That's why I went over that with you a few minutes ago, right? So the pi bond comes from each of the 2 p orbitals that are unhybridized on each one of those carbons, and they overlap side to side. So if you're wondering, well, what does an sp2 hybridized carbon look like? It looks exactly like this. You've got 1, 2, 3 hybridized sp2 orbitals, and then you also have the unhybridized p orbital that's shown here. So if you have a second carbon atom next to it that's sp2 hybridized, they're going to overlap side to side, the 2 p orbitals, to form the pi bond. So if you're wondering, what the hell does that look like? Okay, pardon my language. It looks like this. So here's one carbon. So if you're like, oh my goodness, what is this thing? Hold on, let's watch the whole show before we make any harsh judgments, okay? Let's just focus on one side of it, okay? What they're showing you here is an ethylene molecule. This is the molecule of C2H12. H4. We actually drew the Lewis structure of this earlier on. So what I have here is this. It's just showing you the orbital overlap diagram. So look, each carbon is sp2 hybridized. Here's one sp2 orbital, here's the other sp2 orbital, and here's the third sp2 orbital. So the other carbon on the right is the same thing, 1, 2, 3 sp2 orbitals. Each one has one electron in it. They're overlapping with the 1, 2, 3, 4 hydrogen atoms. Here they are, 1, 2, 3, 4. Okay, and then I'm just going to delete those just to clear it up. Then the pi bond, which is the other bond, right, that results from the overlap, the side-to-side overlap of the two p orbitals. Now, if you're like, well, Mr. Dion, there's a p orbital and there's a p orbital. They are not overlapping, man. They're not touching. No, it doesn't look like they are in the picture, but the way that we show that they are, the way that I show it, is I draw lines in between them like this, and I say, well, they actually are touching technically, okay, even though it doesn't look like they are. So those two, and if you're like, well, no, that's overlapping in two spots. That's two bonds. No, no, no. They're overlapping in two spots, and that forms one bond. So this blue circle that you see right here with one little line in it, that's represented by this. And you're like, well, it's overlapping in two spots. Yes, but when it overlaps in two spots, it makes one pi bond, okay? You see that I'm talking kind of funny because I've explained it many, many times. Give me a thumbs up if you're like 65% of the way with me. And again, this is a review, but I realize it's something that you learned probably in the first half of Gen Chem 1. Awesome. So again, are you going to have to go back in the textbook and review it? Absolutely, okay? If you don't, I'd say my hat's off to you. That would be awesome. But normally students have to do it. So if you're wondering, like, well, the way that you've drawn it with these two p orbitals kind of touching, like you're fake touching, what does it really look like? It really should look like this, okay? Technically, they're supposed to be touching. And if you're sitting there wondering, well, why the heck don't they just draw it with them touching? You can try it yourself. If you draw it with them touching, they get so close that you can hardly tell what's going on in the diagram. So that's why we draw it this way. All right. So you might think, oh, it's not clear, but it actually is drawn that way to clear it up. Anyhow, so there you go. A little bit about pi bonds and where they come from. So this is your pi bond. It's the side-to-side overlap of two p orbitals. Hey, can I ask you another trivia question? And this is an important question. Does anybody know which bond is weaker? Is it the sigma bond or the pi bond? Which one is weaker? Weaker. Yeah, absolutely. So we'll put here, sigma bond is stronger than pi bond. Absolutely. It's counterintuitive, isn't it? Right? Because the pi bond, you might think, well, oh, come on, it overlaps in two spots. So it's twice as strong. No, it's actually significantly weaker. The head-to-head overlap that you get in the sigma bond makes it a stronger bond. So there you go. All right. So let's take a look at a molecule here. Practice problem that says, consider the structure of formaldehyde. I'll help you out with the structure of formaldehyde. It's this. We actually drew it a few slides ago. It's this guy here. It's used as a preservative. It says identify the types of bonds that form the carbon-oxygen double bond. So if we draw, I'll redraw the molecule like this, make it a little prettier. So here's my formaldehyde molecule, like that. Let's see here. Identify the types of bonds that make up the carbon-oxygen bond. Can anybody help me out? What types of bonds make up this carbon-oxygen double bond? And it's not a trick question. It's not loaded in any way. There's a pi bond, that's one. What else? Yeah, exactly. It's got a sigma and a pi, right? So the first bond between any two atoms is always a sigma bond. The second bond between any two atoms is always a pi, yep. What type of atomic orbitals form the carbon-hydrogen bond? So that was question A. We move on to B. So between the carbon and the hydrogen. So first of all, could anybody tell me what's the hybridization of the carbon? What's the hybridization of the carbon atom? And it's not a trick or anything. sp2, absolutely. So it's sp2. And is the hydrogen hybridized? No, you can't hybridize a hydrogen. It's only got one electron in it anyway. So it's a 1s. And so for part B, I would say it's a carbon that's sp2 hybridized attached to a hydrogen. It has a 1s orbital, like that. And then in C asks you, what type of atomic orbitals do the lone pairs occupy? So if we go, let me just redraw the molecule again. If we look at the oxygen, it's got one double bond and 2 lone pairs. What's the hybridization of the oxygen? And it's not a trick question or anything. Hybridization of the oxygen. sp2, right? Because it's got 3 regions of electron density, 1 double bond and 2 lone pairs. So it's sp2, and therefore, what type of atomic orbitals do the lone pairs occupy? The answer is they are in sp2 orbitals. And there you go, my friends. That's the whole kit and caboodle, just like that. All right, give me a thumbs up if you follow me on that question. Anybody with me on that one? Awesome. Cool. All right, so from now on, we can move on to acetylene. And we covered the hybridization of a carbon when it has 2 regions of electron density. It's sp hybridized. So just to make sure we really understand this, the first bond between any 2 atoms is a sigma bond. So that means how many pi bonds do I have between the carbons in acetylene? I have 2 pi bonds, don't I? Yeah, absolutely. This is a pi bond, and this is a pi bond. So 2 pi bonds in acetylene. Now, if you're wondering, how do you make an sp hybridized orbital? Well, you only need 1 s orbital and 1 p orbital. So you mix 1 of each, and you make 2 degenerate sp orbitals, as we see here. And then you're like, well, what about the unhybridized 2p orbitals? Well, what would they be used for? The reason you need 2 of them is because you make 2 pi bonds, right? One of them is used for a pi bond, and the other one is used for a pi bond. Now, if you're sitting there thinking, okay, I saw the sp2 hybridized carbon that had 3 sp2 hybridized orbitals and 1 unhybridized p orbital. What the heck does it look like when you have something that's sp hybridized? Good question. It would look like this. So if you're wondering, what the heck is this, man? What's being shown here is this molecule. This is acetylene. It's this molecule right here, okay? That's what this is. Nothing more than that. So what does the carbon look like? I'll try to draw it here maybe. It's going to have, it's not really enough room. Let me just expand this, okay? What is the carbon going to look like? You have your carbon. It's going to have 1 sp hybridized orbital, another sp hybridized orbital, okay? Then it's going to have 1 p orbital. I'm going to draw the 2 phases the way that they've drawn them here. So you're going to have 1 p orbital that's going to look like this. So we'll have a p orbital like this, okay? And the other p orbital is perpendicular to this p orbital. So you're going to have to bear with me. Mr. Dion is not an artiste. One lobe is going to be going in the back like that, and the other lobe is going to be coming out in front like that. So again, this would be a P, and this would be a P, like that. So what I've drawn there is kind of like this part, okay? So you take the 2 carbons, you put them together, you connect the 2 sp hybridized orbitals. So this is an sp, this is an sp. You make a sigma bond. This is an sp, this is an sp, overlaps with the s on the hydrogen to make the other sigma bond. So these are the 1, 2, 3 sigma bonds, right? 1, 2, 3 sigma bonds. And then you have 2 pi bonds, 1, 2. Those are shown by the overlap here between these 2, this one and this one. And then you have this one in the front and then this one in the back, okay? Like that. So there you go. That's the orbital overlap diagram for something with a triple bond. Is that enough information for you or what? You know, the first college that I taught at was in Canada, and we used to make the students draw these orbital overlap diagrams. You can imagine how fun they were to grade. So we don't make our students draw these. However, I think that if you go through the assigned practice problems, and they're not assigned for value, these are for your, evaluation for yourself. I think I put some problems in there that I recommend trying where you have to draw these. And so even though I'm not going to ask you to draw one of these in a multiple choice exam, I highly recommend giving it a try, okay? So that it really solidifies your understanding of what hybridization is. All right, let's take a look at a question here. Nematin is an interesting compound. It says nematin was first isolated from the fungi Poria tenuis and Poria corticola in the 40s and was shown to possess potent antibacterial. So this is some kind of antibacterial compound. However, its structure was not verified until it was made in the lab much more recently. I don't know what the number 7 there is for. Determine the hybridization state of each carbon atom in nematin. I'm pretty sure we can cover this one rather quickly. If I highlight, let's say, this carbon in yellow, could anybody tell me the hybridization of this carbon? It's got 2 reds, a triple bond, and a single bond. It would be, thank you, Pablo, it's sp. All right, so anything that has 2 reds is going to be sp hybridized. So that would mean that this carbon is sp, this one's sp, this one's sp, this one is sp. 2 double bonds also counts as 2 reds. Are there any other sp hybridized carbons in here? I would say no. What if I highlight this one in red? What would you say is the hybridization of this carbon in red? It's got 3 regions of electron density, a double bond, and 2 singles. Yes, you guys are faster than me. It's an sp2. So I'd say that this one is also sp2. This is sp2. What about if I was to highlight this carbon in green? What would the hybridization of the carbon in green be? It's got 4 regions of electron density. Absolutely, it's sp3. And so I'd say this carbon is also sp3. This one is also sp3, just like that. So I think, there you go. We did it. Can we try another one? Let's just try. Could we do this oxygen in the red circle? What's the hybridization of this oxygen? And it's not a trick or anything. It's sp2. Yeah, sp2. Let's try one more. What about this oxygen here in the blue circle? What would its hybridization be? Yes, sp3. Good. sp3. Wow, I think we covered everything in there because the hydrogens aren't hybridized. So, wow, we really knocked everything out of the park on that one. All right. This is a question that will usually come up on a final exam. Or, if you're MCAT minded, they love to ask questions about bond length and bond strengths. And this is something that students are usually very good at remembering. And that is, first of all, when it comes to bond length, if you look at the trend for bond length, it's simply this: as you go from a single to a double to a triple bond, what we see is that the bond length gets shorter and shorter. Okay, it gets shorter and shorter. And the reason they get shorter is because as we have more orbital overlap, the atoms get closer and closer together. And then you can also imagine that as we bring our atoms closer and closer together, as we add more and more bonds, that the bonds get stronger and stronger. So as we go from a single bond to a double bond to a triple bond, the bonds get stronger and stronger. So what are the trends? As we add bonds, the bonds get shorter and the bonds get stronger. Give me a thumbs up if you'll remember that for me. More bonds equals shorter and stronger. All right, awesome. Well, let's move on from there. Let me just make some notes here. I don't want to leave any stone unturned. All right, let's take a look at this question. It's not meant to be a trick question. It says rank the indicated bonds in terms of increasing length. I'm going to call this one bond. Why don't I label it like this? We'll call this A. We'll call this B. We'll call this one C. We'll go longest to shortest. So which one's going to be the longest bond here? Anybody? A would be the longest. Which one's going to be the shortest? Yeah, awesome. And then B will be somewhere in the middle. Great, wonderful, awesome. That's one I would expect everybody to get that, nail that one. All right. So, moving on from hybrid orbital theory, kind of the logical next step, excuse me, would be to take a look at molecular geometry, right? When we study shapes. So you guys probably remember from general chemistry, you studied linear, trigonal planar, trigonal pyramidal, tetrahedral, all that stuff. And you even studied things like trigonal bipyramid, the octahedron, and all those things. So the only molecular geometries that we cover go up to a steric number of 4 in this class. So we don't cover any kind of octahedral or trigonal bipyramid or seesaw. Those things don't come up in this class. But you have to remember what VSEPR is, right? It's valence shell electron pair repulsion, right? The idea is that electrons, whether they're unpaired in a lone pair or whether they're in a bond, they seek to repel each other because they have negative charges. They want to be as far away from each other as possible. And so when we're determining molecular geometry, the first thing we can always do is look at steric number. And a steric number comes from the number of bonds and the number of lone pairs. So if we look at something like methane or ammonia or water, you can see that these all have a steric number of 4 because they're all surrounded by 4 regions of electron density, right? So again, steric number is associated with regions of electron density. So even though they all have the same steric number, do these 3 molecules have the same molecular geometries? The answer is no, not at all. Does anybody remember what the molecular geometry of ammonia is? Does anybody remember that one? You would have seen it in general chemistry, I'm sure, at least probably more than once. Anybody? Yeah, it's trigonal pyramidal, absolutely. Right, so trigonal pyramidal. And what about the molecular geometry of water? Who remembers that one? What's the molecular geometry of a water molecule? It's bent, right? So bent. And then methane, which we looked at earlier on, that's tetrahedral. And so even though they all have the same steric number, what do they have different? They have different numbers of bonds and different numbers of lone pairs, right? And so we've already covered steric number. And now steric number is related to regions of electron density. And so if we have a steric number of 4, then we have a hybridization that is sp3. If we have a steric number of 3, then we have a hybridization that's sp2. If we have a steric number of 2, it's sp. So again, steric number is the same thing as regions of electron density. So we've already covered hybridization, but what about our molecular geometry? Well, remember that molecular geometry only considers bonds. So I'm going to put under molecular geometry bonds, not lone pairs. So when we're considering molecular geometry, the only thing that we look at is bonds. So with methane, it has 4 bonds, therefore it's tetrahedral, whereas ammonia only has 3 bonds, and so we consider it to be trigonal pyramidal, and water only has 2 bonds, and so we consider it to be bent. Now, even though their electron geometry is the same, because electron geometry, so we'll put electron group, considers bonds and lone pairs, so I'll just put LP for lone pairs. Even though these all have a tetrahedral electron geometry, their bond angles are going to be slightly different because the lone pairs cause greater repulsion and force the atoms a little bit closer together. So when we look at the bond angle in ammonia, we see that it goes from 109.5 to 107. All you need to know for this class is that it's going to be a little bit less than 109.5 because of the extra repulsion of that lone pair. And then when you go to 2 lone pairs in a water molecule, it drops down even more because you have 2 lone pairs that aren't bonding, and so they're going to push those bonds together even closer. All right, so let me review one more thing with you, or something. Let me review something with you before we move on to the next slide. When we're talking about molecular geometry, we're talking about bonds only and not lone pairs. And when we're talking about electron geometry, we're talking about bonds and lone pairs. I cannot stress this enough. You need to know the difference between the two. All 3 of these molecules have the same electron geometry. They are all tetrahedral. they have different molecular geometries, right? Because they have different numbers of bonds and lone pairs. All right, so every once in a while I'll have a student say, do you have this summarized in a table somewhere? Sure, here you go. Everything that you'll need to know in terms of molecular geometry is on this slide. Again, we don't look at steric numbers of 5 or 6 in this class. That's a general chemistry topic. It is not covered in this class whatsoever, so don't worry about it. If you have 4 bonding pairs and no lone pairs, so if you have 4 bonds, no lone pairs, you have a steric number of 4. In that case, your molecular geometry and electron geometry are the same thing. So where it says predicted arrangement of electron pairs, that's your electron geometry. Where it says predicted molecular geometry, that's your molecular geometry, obviously. If you have 3 bonds and 1 lone pair, then you have a tetrahedral electron geometry, but a trigonal pyramidal molecular geometry. If, like the water molecule, you have 2 bonds, 2 lone pairs, again, your electron geometry is still tetrahedral, right? That doesn't change when you have a steric number of 4. But now your molecular geometry, which only considers the bonds, is bent. And then we have the examples where you can have trigonal planar or linear. So you need to know those ones as well. All right. Again, this is a little more review of the exact same thing where it covers steric number, hybridization, and molecular geometry. And so you need to be aware of all the molecular geometries that are covered on this slide and this slide, which are the exact same thing, okay? So again, if you're like, boy, what about the octahedron and the square-based pyramid and the square plane? Those are not covered in this class whatsoever. They're never going to come up on a quiz or on a final exam. They're never, well, they might come up on an MCAT or something because that would cover general chemistry, but they won't come up in organic chemistry. All righty. So with all that in mind, let's see if we can use VSEPR to predict the molecular geometry for the following structure. So let's see here. If we have this thing, this is called a borohydride ion. The name isn't important. What's the steric number of the boron? Anybody? It's got 4 bonds, no lone pairs. It's not a trick. Yeah, it's got a steric number of 4. Therefore, what's its molecular geometry going to be? Tetrahedral, yeah. Tetrahedral. What's its electron geometry going to be? And again, it's not a trick question. I'm never going to try to fool you. Thanks, Hannah. Same. I like the way you put it. Same. Tetrahedral. And if you're sitting there going, hey, could I practice drawing a tetrahedron? Sure, do it. You could say, okay, I'm going to have 1 hydrogen going up, 1 hydrogen in the same plane. I've got 1 going in back. Got another one coming out in front. Like that, put in my negative charge. My bond angle is around 109.5 degrees. There you go. Beautiful. All right, what about this one here? This is a boron trifluoride. But our steric number is what in this case? Again, it's not a trick question. That's right. It's 3. So my molecular geometry is going to be what in this case? Got 3 bonds, no lone pairs. Trigonal planar, absolutely. Trig planar. And what's my electron geometry? Where's Hannah? Hannah, what's my electron geometry? Same. That's right. Trig planar. Thanks. Great. Awesome. There you go. All right. So that brings us to dipoles and molecular polarity. You know what? We've actually touched on this topic quite a bit. Remember the whole thing where we had the delta plus and the delta minus, and we identified this bond as being polar, right? Because it had a difference, right? If you have a polar bond, remember we said it had a difference in electronegativity of 0.5 to 1.7-ish, something like that. Well, there is a way to quantify dipoles, like which one is stronger than another, using what's called a dipole moment, and that's measured in debye's. Now, in the textbook, it goes into what a debye is, how it's defined. I recommend reading it. However, I'm not going to ask you any questions about calculations with debye's. I think the only thing you would want to know in this class is that the higher the dipole, or the stronger the dipole is, the greater the dipole moment would be. So it's going to be a higher number. And that's really all you need to know. Now, something that you've got to be able to do in this class is add vectors together. So let's say we take a molecule like this. This is called dichloromethane. If you look at the two polar bonds, you see these two arrows. If you tally up or add up those two arrows, if you tally up this arrow and this arrow, what you end up with is a net dipole in this direction. Now, if you're wondering how do you add vectors together, if you studied physics, you know that it's tip to tail. Has anybody ever heard the tip to tail method? Yes, no, toaster? Yeah, okay. So some people have heard the tip to tail method. Now, if you've never heard of the tip to tail method, I'm going to do my best to, and I'll probably embarrass myself, but whatever, I don't care. Where am I? How do I go back here? Stop presenting. I'm going to switch over to my camera just for a second here. Can everybody see me? Can you guys see me? No, you can't see me? That's weird. All right, well, I have my camera on, but it's not working for some reason. So let me try this. How about now? Can you see me now? Okay. So I don't know how to make myself full screen. It's worse. Okay, well, maybe I won't be able to talk with my hands. Okay. But anyhow, all I was going to say is if you have whatever you did before it worked. I'm not sure. All right, we'll go back. Let's go back to the slides. Anyhow, I can't show you with my hands, I guess. I can't figure that out at the moment. But the tip to tail method is nothing more than if you take this vector and then you add it. So if I redraw this vector, I'll draw it in blue. So if you add the tip of one to the tail of the other, so you'd have this one kind of like this, maybe like that. So I added the two vectors together. Then the resultant vector is you connect them, right? So you end up with something in this direction, which is what you get like this, okay? So that is the tip to tail method. But the idea is if you imagine, if you have something pulling, in this direction and then something pulling in this direction, well, overall, it's going to pull in that direction like that. So you've got to be able to add vectors together in your mind a little bit to get a net dipole moment. So you can see the net dipole moment in something like ammonia or the water molecule that we have on the bottom right here. So you've got to, in order to be able to determine whether a molecule is going to be polar or not, though, you've got to be able to unequivocally say what its molecular geometry is, right? Because let's say you drew a water molecule like this. Okay, if you drew H2O like that, you'd say, well, that molecule looks like it's nonpolar because I have a dipole going this way and a dipole going that way, but don't they cancel each other out? And the answer is no, they don't cancel each other out because water is in fact a bent molecule. Give me a thumbs up if you follow me on the rationale there that you've got to understand molecular geometry good before you can make a decision about polarity. Good, so don't always just take a molecule at face value. You've got to evaluate molecular geometry before you make any decisions about polarity. All right. Something that you'll see in our textbook from time to time is what they call an electrostatic potential map. An electrostatic potential map, or an EPM. And EPMs can be used to show regions of electron density inside a molecule where more electron density is found. Say you have a molecule like this one here, chloromethane. Well, you can see that we have a polar bond in here. Most of the electron density is going to lie on the chlorine. And so they use the color red or orange to show you that, there's most electron density here. And then they use like a light blue a dark blue color to show you that it's very little electron density around the carbon. They're useful from time to time. I don't use them a whole lot, but the book uses them from time to time to explain different concepts. So just so you know what it is, it's just to show you where there's most of the electron density and very little of the electron density in a molecule. And it helps you predict reactivity sometimes when you're trying to learn that. So that's an EPM. Now, going back to the concept of the debye, which is a unit of measure of polarity of a bond, I told you you are not going to be asked to do any calculations with respect to dipole moments. All you need to know is if you were to compare some molecules like acetone, chloromethane, water, methanol, etc., the higher the dipole moment, the more polar the molecule. So let's say you compared, I don't know, acetone to ammonia. Both are polar, but you can see the acetone is 2.69 debye, ammonia is only 1.47, and therefore acetone is going to be more polar. And if you're wondering, hey, look at these two things down here, they have 0 debye. Does that mean they're completely nonpolar? The answer is yeah, absolutely. There's no dipole in these molecules whatsoever. Completely nonpolar molecules. All right. So what we're going to do now is we're going to take a short break again. And what I want you to do during the break is tackle this problem. Question 1.31, it says identify whether each of the following compounds exhibits a molecular dipole moment. And if it does, try to indicate the net direction of that molecular dipole. So we'll take a break for a few minutes and then we'll come back and we'll tackle this problem, question 1.31.